Imagine a metal tube weighing 412 tons. That's heavier than 58 adult elephants, filled with 500 people, their luggage, and enough fuel to fill 900 bathtubs. And it flies across an entire ocean without stopping. But here's what's wild. The fuel that makes this possible? It's almost identical to the stuff your great-grandparents used to light their kitchen lamps in the 1800s. I'm talking about kerosene. Meanwhile, gasoline, a fuel that's more powerful, burns hotter, and is literally cheaper, doesn't power a single commercial jet in the sky. Sounds backwards, right? But once you understand how kerosene is actually made and what happens to gasoline at 35,000 feet, you'll realize this old-fashioned fuel might be one of the most perfectly engineered substances humans have ever mass-produced. And by the way, if you're the kind of person who gets excited when something finally clicks into place, you're gonna want to stick around for this one. Drop a like right now if you're ready to see fuel in a completely different way.
Let's rewind for a second. Before the Wright brothers, before jet engines, before anyone even dreamed of crossing the Atlantic in 8 hours, kerosene was already famous. In the mid-1800s, people were distilling it from coal and using it to light streets, homes, and factories. It was the fuel of the Industrial Revolution, not for machines, but for light. Fast forward to today, and we're still using it, except now it's helping 100,000 flights take off every single day. But here's the thing, kerosene doesn't just come out of the ground ready to burn. It has to be made. And the process? It's like sorting a messy drawer, but with fire. So how do you take thick black crude oil, stuff that looks like tar, and turn it into crystal clear jet fuel? Imagine crude oil as a smoothie made of 100 different ingredients all mixed together. Your job, separate them without ruining any of it. That's what happens inside a fractional distillation tower, a giant steel column that can be as tall as a 15-story building. Here's how it works. First, crude oil gets pumped into the bottom of the tower and heated to around 400 degrees Celsius. That's hot enough to vaporize most of it. Now picture this. As the vapor rises up through the tower, it starts to cool. And here's where the magic happens. Different substances condense at different heights, like kids sorting themselves by height in gym class. At the very top, the lightest stuff, gases like propane and butane. A bit lower, gasoline. In the middle, that's where kerosene condenses, right around 150 to 250 degrees Celsius. Below that, diesel. And at the very bottom, the heavy stuff that becomes asphalt for roads. Here's something most people don't know. From 1 barrel of crude oil, that's 159 liters, only about 10% becomes kerosene. The rest gets turned into everything else: gasoline, diesel, plastic, even the wax in your candles. But wait, it's not ready yet. That kerosene still has sulfur, water, and impurities that would destroy a jet engine. So it goes through another round of chemical treatment, gets scrubbed clean, and then here's the key part. Special additives get mixed in. Antifreeze agents, so it doesn't turn into wax at -60 degrees Celsius. Corrosion inhibitors, so it doesn't eat through metal fuel lines. Only then does it become Jet A or Jet A1, the stuff that actually goes into airplanes. The kerosene that doesn't meet the grade gets sold off for lamps, heaters, or cleaning greasy engine parts. But here's the question nobody asks. If gasoline also comes from crude oil, also gets refined, and packs more punch per liter, why don't we just use that? And honestly, if you're curious where this is going, go ahead and subscribe, because what I'm about to explain next is going to change how you think about flying forever.
All right, let's talk about what would happen if you tried to fuel a passenger jet with gasoline. Spoiler, it would be a disaster. Here's the issue. When a plane climbs to cruising altitude, about 10 kilometers up, the air pressure outside drops to less than a quarter of what it is at sea level. And gasoline? It loves low pressure. It evaporates fast. So here's what happens. The liquid gasoline in the fuel lines starts turning into vapor. Not all at once, but enough to create bubbles, like when you shake a soda bottle. Now imagine trying to drink through a straw that's half filled with foam. The liquid doesn't flow smoothly anymore. It stutters. It stops. In an airplane, this is called vapor lock. And when vapor lock happens mid-flight, the engine doesn't get a steady stream of fuel. It chokes, and in the worst case, it shuts down. Think of it like trying to drink a milkshake through a straw full of air pockets. You're sucking, but nothing's coming through. That's what the engine experiences. Now imagine that happening at 35,000 feet over the Pacific Ocean with 300 people on board. Yeah, that's why we don't use gasoline. But wait, it gets worse. Gasoline has a flash point of around -43 degrees Celsius. That means even in freezing cold weather, gasoline vapor can ignite from a tiny spark. Kerosene has a flash point between 38 and 72 degrees Celsius. That's a massive difference. Now think about this. A Boeing 777 can carry up to 180,000 liters of fuel. That's enough to fill an Olympic swimming pool halfway. On a long-haul flight from New York to Tokyo, the plane burns close to 100 tons of fuel. That's nearly 1/3 of the plane's total weight at takeoff. If that fuel were as flammable as gasoline, you'd essentially be flying inside a giant lighter, just waiting for a spark. Kerosene, on the other hand, is stable. You can hold a match near it and it won't ignite unless you heat it up significantly first. It's designed to be hard to light. That's not a bug, it's a feature. Okay, so kerosene doesn't evaporate easily, and it's way safer. Got it. But there's one more thing gasoline can't handle, and it's the reason even military jets switched to kerosene decades ago.
Let's talk about where airplanes actually spend most of their time. Way up in the sky, where it's colder than your freezer. At cruising altitude, the outside temperature regularly drops to -40 to -60 degrees Celsius. That's colder than Antarctica in winter. And here's the thing, if your fuel freezes, it doesn't matter how good your engine is. The fuel turns into a waxy sludge, clogs the lines, and the engine starves. Game over. Gasoline can freeze, but that's not the main issue. It evaporates long before freezing becomes a problem. Kerosene, though, engineers specifically formulated it so it stays liquid down to about -47 degrees Celsius. That's not an accident. That's chemistry tailored to the sky. But here's the part that blows my mind, and that most people have no idea about. Before kerosene ever gets burned, it has another job. It's a coolant. Inside a jet engine, the combustion chamber and turbine blades are exposed to temperatures over 1,000 degrees Celsius, hot enough to melt steel. Without cooling, those parts would warp, crack, or straight up disintegrate. So here's what happens. Before the fuel gets injected into the engine to burn, it gets routed through a series of pipes that run right next to the hottest parts of the engine. As the cold fuel flows through, it absorbs heat, just like coolant in a car engine. Think of it like putting a cold drink in your hand on a hot day. Your hand heats up the drink, and the drink cools down your hand. Same concept. By the time the fuel reaches the combustion chamber, it's already done one job, keeping the engine from melting itself. So jet fuel isn't just fuel, it's a coolant, a lubricant, and an energy source all in one. That's elegant engineering. And honestly, if you're enjoying this and learning something new, drop a comment and let me know where you're watching from. I love seeing how far these videos reach, and it actually helps more people discover the channel.
All right, let's zoom out. We've talked about how kerosene is made. We've talked about why gasoline fails at altitude. We've even talked about how jet fuel cools the engine before it burns. But here's the bigger picture. Kerosene wasn't chosen randomly. It was chosen because it checks every single box that aviation demands. Let me break it down. 1. Low volatility. It doesn't evaporate at high altitude, so no vapor lock. 2. High flash point. It's incredibly hard to ignite accidentally, even with 180,000 liters on board. 3. Cold stability. It stays liquid even at -47 degrees Celsius, so the fuel keeps flowing no matter how cold it gets. 4. High energy density. It packs a lot of power per kilogram, which means planes can fly farther without carrying excessive weight. Now think about what a plane has to do. Carry hundreds of people, fly for 12+ hours without refueling, operate in temperatures from +50 degrees Celsius on a runway in Dubai to -60 degrees Celsius at cruising altitude, store thousands of liters of fuel safely even during lightning strikes and turbulence, and do all of this thousands of times without a single failure. Kerosene does all of that, not because it's flashy, not because it's high-tech, but because it's stable, predictable, and reliable. It's the same reason Formula One teams obsess over tire temperature, or why surgeons prefer certain scalpels. When the stakes are that high, you don't want the most powerful option, you want the most dependable one. And in the sky, that's kerosene. Oh, and one more thing most people never think about. Jet fuel is so stable that airport workers can walk on spilled fuel without it igniting. Try that with gasoline, and you'd have an inferno. So there you have it. What seemed backwards at first, using lamp oil instead of gasoline, turns out to be one of the smartest engineering decisions ever made. Kerosene isn't just fuel, it's a multifunctional liquid designed to survive the harshest conditions humans have ever built machines for. And every time you board a plane, you're trusting your life to thousands of liters of carefully refined, highly engineered kerosene. Kind of makes you see it differently, doesn't it? If this video made you think about flying in a new way, or if you learned something you didn't know before, do me a favor and hit that like button. It genuinely helps more people find videos like this. And if you haven't subscribed yet, now's a great time, because if you liked this, you're going to love what's coming next. Speaking of which, here's something even more fascinating. You know how I mentioned jet engines reach over 1,000 degrees Celsius inside? Well, the metal blades spinning in there are hotter than their own melting point. So how are they not just melting? That's a story for another video, and honestly, it's one of the most brilliant engineering tricks I've ever come across. So go ahead, subscribe, and click on that playlist on your screen. There's a whole lineup of videos breaking down machines, vehicles, and systems that seem impossible, but somehow work. Trust me, once you start, you won't want to stop. Until next time, I'll see you in the next one.